Hello everyone. In continuation to our previous discussion on topic corrosion protection methods, which is belong to the course Corrosion Engineering MM304. So today we will learn two more topic for corrosion protection. So second topic, if you remember, the first topic was how we can protect a metal or a metal alloy from corrosion. That was the idea, like if we can coat by either metal or metal oxide, ceramic or organic or any other material on the top surface of that metal and alloy which we want to protect, that will basically separate out that metal with the medium which is causing the corrosion. So if that separation is possible by putting a barrier layer or a coating layer or a painting layer, so that we consider in category. That was the number one, coating method. The second method is corrosion inhibitors. Basically inhibitors means those substances or those chemicals which reduce the corrosion process. So if by any mean we add something, some chemical, some component or substances, and by adding that medium or substances, if we can reduce the anodic or cathodic reaction, then we can say they are working as inhibitors. So chemical substances, they reduce corrosion by either acting as a barrier by forming an adsorbed layer or retarding the cathodic or anodic or both process. So either they are creating a barrier or they are basically slowing down or reducing the rate of anodic and cathodic reactions, or maybe the both. Here you can see a symbol like this is the metallic ions which are tend to have a corrosion, but when they will be having this kind of they have seen the white color, this kind of inhibitors, then they react and then they create some kind of surface layer which protect from the corrosion. So it can be defined as a corrosion inhibitor is a substance that effectively reduces or prevents the corrosion of exposed material in a corrosive environment. Few more things about this. Inhibitors in small concentration are added in cooling water, acid, and steam to maintain an inhibiting surface film. So very small amounts, maybe few ppm to few thousand ppm level concentration we generally add to get the kind of layer over this kind of environment. One more point, like inhibitors that affect anodic or cathodic polarization properties. So you know corrosion is caused due to the reaction at anode, and anodic and cathodic reaction take place at different places within the same material, and due to which we are getting the corrosion behavior. Or maybe material, let's say working as a anode in somewhere, and that is having its own polarization potential. So if we are adding any inhibitor, then it generally reduce that polarization potential. So it affect the anodic or, depending upon the type of inhibitor, cathodic polarization properties, and by reducing these properties, or basically controlling this property, it also reduce the corrosion rate. So see how it works. So more preferred or general mechanism of inhibitors are preferred inhibition or inhibitor anion absorb on the metal surface. So whatever inhibitors is there, they generally absorb at the metal surface. Then after plugging the pore of passive oxide film. So if there is any pores or non-uniformity in the passive film, because that passive oxide film, whatever created on the metal surface, is protecting the metal from corrosion. But if somehow or due to the presence of environment, it is broken down, it is having some kind of pores, pits, or some basically discontinuation is there, then that can be recovered or can be repaired by inhibitors, and promoting reparation of damaged passive oxide or passivating oxide film, and by this process it is able to decrease the metal dissolution. So how we can understand like what kind of inhibitor could be there? So I think this figure will help us to understand this. See, we can divide based on these three, like how it work. So either based on the mechanism. So then we can say either it is anodic, or it is cathodic inhibitor, or it is mix. Means either it is working at anode, or it is affecting the property of cathode, or it is affecting the property of both. So some chemical is there and that is able to do these three functions. Similarly, the environment. So this is the second. If we are taking the consideration of environment, then whether our environment is acid. So if acidic environment is there, then how inhibitor is going to help in and going to reduce the effect of acid. Similarly, if it is having an alkali or alkaline atmosphere, then our environment, then how it is going to work. Similarly, if neutral. And the third mode, we can say the mode of protection, like how it is helping or what kind of protection is it is providing to the metal. So one is by chemical passivators, means chemical is going to attach there at the surface and it is passivate the reaction. Or second is again just adsorption. So passivation is basically slowing down the reaction, and adsorption is also, which is, so adsorption or film forming, both are look like similar, slight difference is there. Both are going to, in one metal is going to attach, but it not maybe making every uniform film. In second case, it may become entire covered surface. So you can say it's film formation, or maybe the inhibitor could be present in the vapor phase only. So thus fourth will be the vapor phase. So all this basically based on this we can say either mechanism based bifurcation or classification can be done, or environment based or mode of protection based. So based on the requirement, we can adopt any methodology or the mix of this methodology to basically design or to utilize or to find out a most suitable inhibitor. How we can calculate the efficiency? So this is the reaction like inhibitor efficiency is determined using formula I efficiency is R0 minus Ri divided by R0 multiplied by 100, where I is the efficiency, R0 represent the metal corrosion rate. So in absence of inhibitor, so without adding inhibitor, whatever the rate is there, that is R0 or R0. And when you are adding the inhibitor, then what is the rate of corrosion, that is known as Ri. So by using this formula, we can calculate how efficient inhibitor, like whether it is able to reduce 50% rate, 40%, 60%, 10%, like depends. So based on this efficiency, we can say like which is the best one, a suitable inhibitor. So now move to the this variety of different whatever we have taken like anodic, cathodic, or mix or environment based. So just very brief intro about these. So first one is basically the anodic passivating inhibitor. So as name suggests, like there is a chemical which is going to affect the anode only, and therefore we are calling the anodic passivating inhibitor. So anodic inhibitor increase anode polarization to the critical passivation potential of the metal or alloy. So basically it increase the potential when you are putting, so anodic reaction is going to slow down. Therefore, we also call it passivating because it's going to slow down the reaction by increasing the polarized potential, or inhibitor because they drastically decrease the corrosion current. Further, these inhibitors are strong oxidizing agent and shift the corrosion potential of the metal in the noble direction with the formation of a passive film. So idea means, let's say if a material is going to corrode at potential -1, then it is going to shift at least -8, -0.7 or -0.8. So depending on what kind of, so that means it is again giving the window of 0.2 or 0.1 or 0.3 volt higher side. So that is, I'm just giving a rough figure, it's not a number. So the idea is if your material is in somewhere here, and if you are able to make shift it slightly lower side, so it is going to have less tendency of the corrosion. So that is the beauty of this kind of inhibitor. It is going to shift the corrosion potential toward the noble direction side. And two type of passivating inhibitors are generally there. The one is oxidizing anions. So one is anions oxidizing, example are chromate, nitrates, nitrites and nitrates, that can passivate steel in absence of oxygen. Second is non-oxidizing ions such as phosphates, tungstenates and molybdates that require the presence of oxygen to passivate the steel. So these two kind of inhibitor is there. Now move to the second. Second is the cathodic precipitation inhibitor, or we can say those who are working on the cathode. So your material is working as an anode. So anodic reaction is responsible for the corrosion. But at the same time, somewhere we are having the cathode, then it's a balance equation, right? It's a full cell. If at one place, if we are having a observation of anode, let's say the material is there and it is going to corrode, then somewhere else there will be a cathode or cathodic reaction. So that if you reduce that cathodic reaction, then also you are reducing this overall cell reaction, because corrosion is an electrochemical reaction, and here the anodic and cathodic both the reaction are taking place simultaneously. So either of one, if you stop or you slower down or you reduce, then we can control the corrosion. So the second case is, now we are going to put some chemical which is able to control or reduce the cathodic reaction. So cathodic inhibitors reduce corrosion by slowing the reaction rate of the electrochemical corrosion cell. Removal of oxygen from the corrosive environment will significantly decrease the corrosion rate, because this can be done through, so how we can reduce the oxygen content? So number one, maybe we can use oxygen scavengers such as sodium sulfite, hydrogen, which react with oxygen and remove it from the solution. So simply just by removing the oxygen, we can passivate the cathode, or we can reduce the cathodic reaction, and it can be achieved by adding some kind of oxygen scavenger agent. Second, maybe we can do the vacuation, de-aeration, like we can just remove out the air by vacuum processing, if it is possible. That's why, depending upon the conditions or our user environment, we can do the devacuumation also, or boiling to the lower to dissolve oxygen concentration. So boiling the lower, the dissolved oxygen concentration will be removed. So that is the another method. So cathodic inhibitors shift the corrosion potential to the anodic direction. So here is the reverse. If it is shifted toward the anodic direction, then it is more better. It is not having high rate to have the reduction potential, or we can say the cathodic reaction. So based on the inhibitor mechanism, this cathodic inhibitor can be classified as cathodic poisons or cathodic precipitates or oxygen scavengers. So basically, based on this mechanism, like how they are going to reduce the reaction rate at the cathode. So first one is the cathodic poison. They basically decrease the rate of hydrogen evolution, reaction by absorption or deposition of sulfide, selenite, arsenide, bismuth, antimony on the metal surface. So if it is deposited, then what is we are reducing at cathode side, we are observing the water basically reduction, or we can say the hydrogen reduction. So hydrogen gas is forming there. If we reduce the hydrogen, means we are reducing the reaction of cathode. So if these kind of deposition, sulfide, selenite or whatever we have put it here, if that is there, then if this reaction is reduced, means it is having the less effect on the cathode. Anodic precipitate is basically compounds such as calcium, magnesium, with precipitate as oxide to form a protective layer which acts as a barrier on the metal. So again, this kind of metal barrier we just creating over the cathode, and therefore we are calling it the cathodic, sorry, it should be C, cathodic precipitates. Oxygen removal or scavengers. These compounds react with the oxygen present in the system to form a product and reduce the corrosion. For example, As plus 3, Sb plus 3 or dissolution of Fe in acid. So by these three different type of mechanism are there, anyone can be selected for reducing the cathodic reaction. So these inhibitors having one issue, and that is basically inhibitor hydrogen recombination. They reduce, so they may cause hydrogen blistering or increase metal susceptibility to hydrogen embrittlement, because hydrogen ions are present, and they may, that ions we are not reducing them to make the hydrogen, so they may attack the cathode. So that possibility is there, or we can say that is issue is there if we are using the cathodic precipitate or cathodic inhibitor based reaction. Now the third category is the mixed precipitation. So here basically we are using a kind of chemical which is affecting the both the process, anodic as well as cathodic, and therefore we are calling it a mix. So anodic inhibitors are slightly more, I would say, dangerous in the sense like if you having a difference in the concentration of that inhibitors, if it is small less, then there could be a very high chance to having a corrosion, and if you added a lot, then maybe it is having the another effect. So that balance concentration or the optimum concentration is very much important. However, cathodic inhibitors are not that much difficult, so that's why it is considered as more safe. So mixed inhibitors are less dangerous than pure anodic inhibitors, and in number of cases they may not increase the corrosion intensity. The most common inhibitor of this category are the silicates and phosphate. So silicates and phosphate based chemical can be utilized as a mixed precipitate. Such inhibitor will have the more advantage that they control both cathodic and anodic reactions. So we are not controlling only one. Now move to the next one. So second category is of the inhibitor is basically based on the environment. So the first example is, let's say if we have the acidic environment. So how we can reduce the effect of acid, what kind of chemical we can use, that we are going to understand here. So one inorganic material we can use such as As2O3, Sb2O3 or many others. I'm just giving one example or two examples here. So these kind of inorganic material we can use that basically reduce the effect of acid medium. Protection is due to the reduction of the electropositive ion and deposition on the metal surface and lowering of the over voltage of main cathodic depolarization reaction. Heavy metal ion is also reported such as Pb, Ti, Mn, Cd base ions for these kind of applications. Second one category is we can use the organic chemicals, and in organic compound which is having a kind of oxygen, nitrogen, sulfur kind of content or multiple bonds are good for corrosion inhibitors. Many organic inhibitors such as amines, aldehydes, alkalides, nitroso compound are also tried as corrosion inhibitors. So either we can use inorganic one or we can use organic one. Both can be used for acidic environment to reduce the effect of acid. Similarly, if we are having the alkaline environment, means the higher pH. So here also we can use some kind of material which can affect, let's say, the metal which form amphoteric oxide are prone to corrosion in alkaline solution. So if you are having that metal which is going to corrode in alkaline solution, then we have to use some kind of compound. So many organic compounds are often used as inhibitors for metal in basic solution. Compounds such as thiourea, substituted phenol, naphthalene, beta diketone, etc. are effectively used as an inhibitor. Then if we are having a neutral solution, means it's a neutral pH, then the interaction of exhibitor with oxide cover metal surface and prevention of the oxygen reduction reaction at the cathodic side take place. So here again some surface active inhibitors has been found, and which is efficient also to basically protect in a nearly neutral environment or solution. So these are basically the base of the environment. Similarly, let's say based on the protection method or the mode. So one is based on the chemical passivators. So what we understand about the chemical passivator, basically they are having a sufficient high equilibrium potential, redox or electrolyte potential, and sufficiently low over potential, because corrosion rate and attainment of the passivity are called chemical passivators. So what kind of chemicals are there? So examples could be nitrites are used as an inhibitor for anti-freeze cooling waters. Similarly, chromates, they are also chemical passivators, are mostly used in inhibitor for recirculating cooling waters. So recirculating cooling waters are there, then chromate based inhibitor we can use. Zinc molybdate is used as an inhibiting pigment for paint. So by mode of chemical passivator, these kind of chemical we can use and they will work as a passivator. Next one we can say absorption inhibitors. So they are organic compound which get absorbed on the metal surface and provide a blanketing effect over the entire surface. So it is again looks like the same as what we talked previously. So basically the category was it's different. The first was based on the basically the environment. The first one was the based on the acidic, anodic, and cathodic and mix reaction, like what reaction we are going to start. Second was what kind of medium is there, and the third one is how they are going to work. So basically the based on the protection method. So if absorption inhibitors are there, organic we can use again, and which are going to absorb on the surface and then protect the material. So effect both cathodic and anodic reaction equally, but in many cases the effect may not be equal. And these are commonly used in acid pickling of hot rolled product in order to remove the black mild scale, and are thus known as a pickling inhibitors also. Example, we can understand here the compound containing lone pair of electrons such as nitrogen, atominamine, and sulfur atom are like these oxygen atoms. These are the similarly the next one is the film forming inhibitor. So here they basically forming a film, a blocking layer or a barrier layer material other than the actual inhibiting species itself, and such material tend to be specific either to cathode or to be anode. So like it's very specific chemical whether we are going to use a cathode or we are going to use anode. Based on that the selection should be there. Zinc and calcium salt are the most common example of cathodic film forming inhibitors. So if we are going to protect the cathode, then zinc based or calcium based salt we can use, and that they will make the film on over the this material will make the film over the that cathode, and it can protect from corrosion. Benzone is commonly example of the anodic film forming inhibitors which inhibit corrosion during the process. And now the last one is the vapor phase. So if vapor phase is also called as volatile inhibitors, they are substances of low but significant vapor pressure. So if high vapor pressure is there and it can be used, the vapor come in contact with surface of the metal and the absorption of the inhibitor take place. So since high vapor pressure is there, so they will go and having the they can may attach at the surface of that metal, or it can present at the metal surface, so the reaction will be passivated. Example could be dicyclohexylamine chromate or benzotriazole for protecting the copper. Similarly, phenylthiourea and cyclohexylamine chromate for brass. So similarly, these kind of different vapor-based inhibitors can also be used. So this was the brief understanding about the inhibitors. So if I would summarize, I would say inhibitors are a kind of chemicals which we add in the environment where our material or metal is there, and it is having a similar function. Either it is passivating the anodic reaction or it is passivating the cathodic reaction. Mean could be different, either making the film or making the surface absorption, or by just reducing the reaction component, like it not going to reduce the hydrogen or not going to accelerate the oxygen formation. So these kind of control over the surface and the reaction is achieved by the inhibitors, and based on this reaction we have also divided into different category. So these also the one idea, like by using the inhibitors we can reduce the corrosion rate. Now we will switch to the next topic, and that is the cathodic protection. So this is also very important topic, and here what we understand about the cathodic protection. So at word itself says, or if you say cathodic and anodic protection. So we want to protect the anode because the corrosion is always happening at the anode. It's anodic reaction. But if we can add some kind of cathode and which can tune the anodic reaction or which can control the anodic reaction, so by this process we will be able to control the corrosion rate, right? So therefore we are calling it a cathodic protection, means by doing something on cathode we are going to control the anodic reaction. Here we can say the cathodic protection. So how we define it? Cathodic protection is defined as the reduction or elimination of corrosion. How? By making the metal a cathode by mean of impressed current or sacrificial anode, usually magnesium, aluminium or zinc. So idea is that if we use another metal, make a cathode, and then if we can have the either a sacrificial anode we call, or we can say it's impressed current. So in both the cases it is going to protect the material. And bottom you can see I have taken the figure from this reference, which shows how we can protect the underground pipeline. So you can see here the example, this is the underground pipeline, this one, and here see this is a metal connection basically to give a electrical conductivity, and this is the electrical conductivity if you can see this point. Similarly here this is a material which is a cathode, which is we are calling it a sacrificial well anode, and if you just connect with the pipe, then what will happen? If this material is less noble, in electrochemical series, less noble means if you compare this material with respect to this, it is in the lower in the table and it easily get corrode. So what will happen? If whatever electrons are generating here, if that electron can pass to this material, then we can say this material is protected. Means if these two are connected together, so then there will be flow of current and this material will degrade rather than this. So whatever our actual material, this pipeline will be protected due to the presence of this electrode. So that is known as a sacrificial anode. Means this anode is going to sacrifice on behalf of this pipeline. Other way around, we can, so therefore if you can see here like this protection current is there, means this is flowing a current toward this side and therefore this is protected. Otherwise the current flow should be reverse. If current is like this direction, then this material is going to reduce. Similarly the impressed current means either we can apply a voltage and again we can create this kind of current. So that will be the impedance current. So either applying the voltage or just connecting the material. So these are the two way. So let's say understand in further detail. For iron corroding in an accelerated neutral electrolyte, the following reaction takes place. Means iron convert into the iron plus 2 and plus 2 electron. So this is the reaction. Okay. And but if anyhow we don't promote this reaction, so how we can reduce the promotion of this reaction? See, if we already supply some electron to this metal, if some electron we supply to this metal or give a negative bias, so what will happen? It will not have a tendency to have this reaction. So by that mean of process, we can reduce the anodic reaction. And similarly, this hydrogen and oxygen reaction is there, and which is creating 4OH. So this reaction is happening. So corrosion will start only when both cathodic and anodic reaction occur simultaneously. And we can see here the figure. Let's say this is the figure shows the one reaction, and this is figure shows the another reaction. So first one is the anodic reaction. If you remember, we have already discussed earlier, and this is the cathodic plot. So this is the figure where you can find out the E-corrosion value. But say if by applying or connecting these two metal, so by creating a sacrificial anode or by connecting a bias, if anyhow we can reduce this E-corrosion from here to here, then means what will happen? We are going to reduce the current from here to here. So I corrosion will be I dash corrosion. Means if we are able to reduce the potential, since we are applying a potential or we are just making this connecting with the lower potential material, so we are going to reduce the E corrosion. That will reduce the I corrosion, and therefore it will reduce the overall corrosion. So the corrosion rate decrease by cathodically polarizing the cathode in the negative direction from the corrosion potential, and polarizing the system from E corrosion to E dash corrosion with a known potential current. The corrosion current decrease from I corrosion to I corrosion dash. So these all are possible by two methods. One is the sacrificial anode and other one is the ICC, basically our ICS, impressed current system. So now we will discuss all these two processes in the next. Cathodic protection by sacrificial anode. So what is the sacrificial anode? Corrosion protection is accomplished by coupling a less noble, that is more electric negative metal in galvanic series. So just we are connecting with that metal only. Example, let's say the nobler pipeline, which is metallic, in this galvanic couple is cathodically polarized with the less lower metal in anodically dissolved. See here the figure. Let's say this is the pipeline. Are you able to see here? This is the pipeline, and it is just connected with the Mg anode. So now this anode is having the sacrificial nature, and we will call it this is a sacrificial anode. And due to this connection, basically now these two material are having different electrochemical potential, right? So due to that difference in electrochemical potential, there will be a tendency for the current flow. So current will make a circuit. So through this, so we are saying like the current flow like this way. It's just symbolic. So this mean we are able to slow down the reaction of this metal or anodic reaction. So this is the sacrificial anode. Anode is here is packaged in a bag fill consisting of 75% gypsum, 20% bentonite and 5% sodium sulfate. So when we are inserting this anode, this kind of bag filling is also required, because this bag fill absorption absorb the corrosion product and water from the soil to keep anode active. What will happen? Let's say one layer is here, the sacrificial anode is having one layer which is corroded. Now it's form a corrosion product. Now it's not connecting with the environment and not producing its effect. So therefore, if you are adding this kind of composition around the surface, it will always make this anode as a fresh anode. So sacrificial anode are coupled to the pipeline at regular interval based on the current requirement need to protect the pipeline. So it will be connected, or maybe time to time in fixed interval we can connect it. So what kind of material is required, or how we can think of like which is the good one? So requirement for a good sacrificial anode, we have listed few here. So the one is the potential between the anode and the corroding structure must overcome the formation of anode cathode cell on the corroding structure. So basically a cell formation should be there, otherwise we are not able to use this system. When drawing the current, the anode should not be polarized to a large extent. But see, when you are selecting the sacrificial anode, it should not be possible like there should be a very huge difference. Otherwise, this anode will be polarized a lot, and then it will again have a very high corrosion rate. So maybe it's not very durable. Third option is basically point is the anode must have high anode efficiency, that is the current produced by the metal dissolution must be readily available for cathodic protection. Means the idea is that it should not be like it's very small or it's very big. It should be compatible with the anode. See, whatever metal you are going to protect, it is generating some current, right? So that sacrificial anode should be able to handle that much current. So it should be efficient to work as per the material. So according as per the design or the size of your material which you want to protect, this sacrificial anode should be designed. Magnesium, zinc are the predominantly used galvanic anode material for cathodic protection in the pipeline. Corrosion potential difference of the magnesium with respect to the steel is 1 volt, which limit the length of pipeline that can be protected by one anode. So since 1 volt, so even we cannot take infinite long or maybe few kilometer long pipeline and just connect with one, because it's only 1 volt. So how much it can be distributed? So based on that, we have to understand. Now the second one was the basically the impressed current system, or sometimes we also called it ICCP, impressed current cathodic protection. So here what we are doing in first case, we are just connecting to the wire, but here this is even more better because we are just connecting, and if the environment is very much corrosive, then maybe the sacrificial anode will corrode very fast. So what about the duration, like how long we can use it as a protecting layer? So this could be a serious issue. So here it could not be there. Here what we are going to do, we are going to apply an external power supply. You can see the figure. Let's say this is the material which we want to protect. So we are having a sacrificial anode. Here you can see and fill with the backfill. So they even see they have designed very properly. This backfill is there. Then this is the sacrificial anode, and this is the material which we want to protect. So just connect with the DC power supply. So what we are doing, basically we are supplying the electron to the system, electron to the metal. So if we are having already having the excess electron, then metal is not going to oxidize, it is not going to produce further electron because already plenty of electrons are available, or it's negatively biased. So by this process we can protect the metal. So external DC current is used to cathodically polarize the pipeline. Cathodically polarized means to provide the negative bias. An impressed current system can be used to protect bare or poorly coated pipeline because of high current capacity. So here we have good chance we can supply like high power voltage and all. Because in case of sacrificial anode, we cannot go more than 1 or 2, 1.5 electron volt difference. Here we are applying, we can apply 20 volt also, 30 volt. But current is need to be monitored, but high voltage or high current can be applied. So iron with 15%, silicon, carbon, graphite are some commonly used anode for pipeline protection. So basically how we are going to select the ICCP system. So few points are here. Advantages. Here no need for an external power source. Basically in the case of sacrificial anode. Less complex installation, uniform distribution of current, minimum maintenance, minimum cathodic interference. If we are using the sacrificial, I'm not talking about ICCP. So what is basically the good and bad point, or limitations and advantages? But in case of sacrificial anode, these are the plus point here. But here the limitations are also there. The current output is limited because we don't have too much voltage variation. It has a limited driving potential, therefore the protection for the bare steel is limited. Poorly coated structure may not be very well protected. The system is ineffective in high resistive environment. But if we are talking about the ICCP, so it has some other advantages as compared to the sacrificial anode. And the first advantage is the system can be applied with a wide range of voltage and current requirement. So of course, either better chance is there. High current can be impressed with a single ground bed, only one sacrificial node, and then we can apply a very high current. Single installation can protect large metallic surface. Uncoated and poorly coated structure can be effectively protected by using ICCP. Voltage and current can be varied to meet the changing condition with the time. This is very important. If we are using the sacrificial anode, there is a fixed voltage based on the difference in the galvanic potential. But here you can tune. Sometimes you apply 2 volt, let's say, sometimes you can apply 3 volt if there is a change in the conditions. But here also the limitations like overprotection lead to coating damage and hydrogen embrittlement. Let's say if it is overprotected, maybe we apply a high voltage. So we are not doing any hydrogen reaction, cathodic reaction. So if no cathodic reaction, then it may have the presence of hydrogen ions, and then hydrogen can have the hydrogen embrittlement kind of problem. The system is affected by the interference problem. The external power is necessary. So in maybe some places we are not able to provide the external power. Thus the system is vulnerable in power failure. And if power failure, then if power failure is there, then it's no use. So I think that was about these two technique, cathodic protection. So I will just revise here. Cathodic protection means we are going to protect the anode by creating by creating a cathode, but creating a cell within the system so that the local cell formation should not be there in metal. Otherwise, what will happen? Metal will form somewhere in anode and some other position as a cathode, and a local cell formation will be there, and that will initiate the corrosion. But if by some mean we are creating an basically artificial cell where another cathode is there, so anode is going to be protected. So that cathode, if it is directly connected, then it's not a kind of cell, then we call it just a sacrificial anode. But if by some potential or maybe applying by a voltage, we are applying the electrode, then we are calling it basically the impressed current ICCP based system. And it has some more advantages as compared to sacrificial anode. So today we discussed the two process. One was the inhibitors and second process was the cathodic protection. So now we have only one or two more method. So I will come in the next lecture with that discussion. So now thank you very much.